Imagine a highway at rush hour. You're cruising in your autonomous vehicle, smooth and steady, until suddenly a car swerves into your lane from the adjacent one. No warning. No signal. Just a split second to react. This is the cut-in maneuver, one of the most dangerous and unpredictable scenarios in autonomous driving. Traditional collision avoidance systems often fail here. Why? Because they rely on rigid rule-based logic that can't adapt to real-time chaos. But what if we could build a system that doesn't just react, but anticipates? This is exactly what this research tackles. A new intelligent collision avoidance system that combines time-to-collision, TTC, metrics with deep learning, and a powerful probabilistic framework using Gaussian modeling to predict and prevent crashes in cut-in scenarios before they even happen. Let's break it down. Hash the problem, why cut-ins are so dangerous. When another vehicle suddenly cuts into your lane, the ego vehicle, your autonomous car, faces an extreme time-pressure situation. The available space and time for evasive action collapse rapidly. Traditional TTC-based systems calculate the time until collision assuming constant velocity and straight-line motion. But in real life, vehicles accelerate, brake, change lanes unpredictably, and that's where the model breaks down. The core issue: static assumptions. TTC is a great metric in theory, but in dynamic traffic, it's too simplistic. It doesn't account for uncertainty, sensor noise, human erratic behavior, sudden braking, or even weather conditions like rain or fog. So how do we fix it? Hash the solution: a hybrid intelligence system. The proposed system is not just another rule-based algorithm. It's a deep learning-enhanced, rules-based adaptive, RBA, framework that integrates real-time TTC computation with predictive modeling and probabilistic risk assessment. Here's how it works. First, the system continuously monitors 4 critical parameters. Ego vehicle velocity, how fast you're going. Lateral distance, how far the intruding vehicle is from your lane. Longitudinal distance, the gap between front of your car and the back of the cutting-in vehicle. Lateral velocity, how quickly the intruder is moving across lanes. These inputs feed into a deep learning model, specifically a long short-term memory, LSTM, network. Why LSTM? Because it excels at processing time series data. It learns the sequence of events, the evolution of distance, velocity, and position over time, allowing it to predict future states with far greater accuracy than static models. But here's where it gets really smart. Instead of treating TTC as a fixed threshold, the system uses a Gaussian probability model to estimate the likelihood that TTC will fall below a critical threshold, say 2 seconds, indicating imminent collision. Think of it like this: rather than asking, is the TTC below 2 seconds? The system asks, what's the probability that TTC will drop below 2 seconds in the next 0.5 seconds? This shift from deterministic to probabilistic thinking is transformative. By modeling input uncertainties, sensor inaccuracies, fluctuating speeds, unpredictable human behavior, as Gaussian distributions, the system can quantify risk in real time. It doesn't just detect danger, it predicts the chance of danger. And because the Gaussian model captures variance, it can identify when the risk is not just high, but increasing rapidly. That's crucial for triggering timely evasive actions. Hash the safety logic, a multi-stage decision engine. The system operates through a layered safety check. Step 1, lateral safety. Calculate the lateral distance between vehicles, subtract half the width of both. If the result is less than the safe lateral threshold, say 1.6 meters, the system flags a potential conflict. Step 2, longitudinal safety. Compute the longitudinal gap, subtract vehicle lengths. Then adjust the safe distance, dynamically based on ego velocity. High speed, bigger buffer. Low speed, smaller gap allowed. Step 3, velocity difference. Calculate the relative speed between the ego and cutting-in vehicle. This determines how quickly the gap is closing. Step 4, stopping time margin. Now comes the key insight. The system computes a stopping time margin, based on reaction time, deceleration capability, and current speed. If the time it would take to stop is longer than the time available, the system concludes the situation is unsafe. Step 5, final safety check. Only if all 4 conditions pass is the cut-in deemed safe. Otherwise, the system triggers a response. Hash the response, not just braking, but smart maneuvers. Here's the innovation: the system doesn't default to one action. It evaluates multiple responses. If the predicted TTC is low and deceleration alone can avoid a crash, then it applies controlled braking. But if the surrounding traffic makes braking unsafe, say a car is close behind, then the system considers a safe lane change. How does it decide? The deep learning model assesses: is there enough space in the target lane? Are there vehicles approaching from the rear? Is the lateral velocity too high for a safe maneuver? It weighs all these factors in real time and selects the optimal evasive action, whether that's braking, lane change, or a combination. This adaptive strategy is what sets it apart. It's not just reactive, it's anticipatory. Hash validation, simulations that prove the power. The system was tested using the Heidi dataset, a rich, real-world trajectory database of German highway traffic captured via unmanned aerial vehicles. The simulations included sudden aggressive cut-ins, gradual smooth lane changes, Emergency braking scenarios. Urban traffic with frequent lane shifts. The results were striking. Compared to traditional TTC-based methods, the RBA system reduced collision risk by over 40% in high-stress cut-in events. It also significantly improved driving smoothness, reducing harsh braking and abrupt maneuvers. But the most revealing insights came from sensitivity and uncertainty analysis. Sensitivity analysis, what really moves the needle. Sensitivity analysis reveals how changes in key inputs affect TTC and overall safety. For example, longitudinal distance has a direct, proportional effect on TTC. Halve the gap. Halve the time to collision. Relative velocity has an inverse relationship. A small increase in closing speed drastically reduces TTC, especially when speeds are similar. Lateral distance doesn't directly impact TTC, but it indirectly affects it by influencing reaction time. A tight lateral gap forces earlier, more urgent responses. And here's the critical finding. When relative velocity is low, small changes have outsized effects on TTC. That's because the system is operating near the edge of its reaction window. A 1 km/h increase in closing speed can turn a safe scenario into a critical, one in less than a second. This insight is vital for designing driver assistance systems. It tells us that precision in velocity estimation is paramount, especially in low-speed, high-density environments. The Gaussian advantage, real-world robustness. Now, let's talk about why the Gaussian model is so powerful. In real-world driving, we don't have perfect data. Sensors drift. Drivers behave erratically. Weather changes. The Gaussian model handles this by treating uncertainty as a distribution, not a single value. When you plot TTC over time as a Gaussian curve, the mean, mu, tells you the average risk level. The standard deviation, sigma, tells you how consistent the system is. A narrow, tall curve. Stable, predictable behavior. A wide, flat curve. High variability, meaning the system sometimes operates in risky zones. The RBA system showed a low sigma, indicating consistent, reliable performance, while maintaining a high mu, meaning it operates in safer regions of the risk spectrum. In contrast, traditional TTC models often had high sigma values, indicating erratic behavior. They'd be safe most of the time, but occasionally they'd fail catastrophically. The Gaussian approach makes the system robust under uncertainty, exactly what you need on a rainy night with a distracted driver cutting in at 80 km/h. Conclusion, towards smarter, safer autonomous driving. This research proves that combining deep learning, dynamic TTC computation, and probabilistic risk modeling creates a collision avoidance system that's not just better, it's fundamentally smarter. It doesn't just react to danger. It predicts it. It doesn't just follow rules. It learns from experience. It doesn't just assume the world is stable. It models uncertainty. The future of autonomous driving isn't just about faster processors or better sensors. It's about smarter decision-making, systems that understand the nuances of human behavior, the chaos of real traffic, and the math of risk. And this RBA framework, powered by LSTM, guided by TTC, and grounded in Gaussian uncertainty, represents a major leap forward. Future work will focus on real-world validation, integrating multi-sensor fusion, LiDAR, radar, camera, and exploring multi-agent strategies for complex intersections and urban grids. But one thing is clear, when the next cut-in happens, the car won't just brake. It will think and act like a skilled human driver but with superhuman precision. If you're passionate about AI, robotics, or the future of transportation, hit subscribe. Because the next breakthrough in autonomous safety might just be a few lines of code away.